Hello, everyone. I'm Don Sutton, Sales Manager for the U.S. and Canada. Tiger-Sul Products is a global leader in sulfur bentonite since 1964. We have built a reputation on the highest quality products, extraordinary customer service, a professional and responsive sales team, and a commitment to research and education. On behalf of the entire Tiger-Sul team, we thank you for joining us on this webinar. Sulphur, amending soils with Tiger-Sul products to reduce soil pH. It is my pleasure to be here with Wesley Haun, the presenter of today's webinar. Wesley Haun, Senior Agronomist at Tiger-Sul Products. He coordinates soil fertility and crop nutrition research with various research organizations in the United States, Canada, and internationally. He conducts educational programs that emphasize the benefits of a complete plant nutritional management program. Wesley received his Bachelor of Science degree with a major in agriculture mechanism and a master's degree with a major in plant and soil science from the University of Tennessee. His professional certifications include Certified Professional Agronomist, Certified Professional Soil Scientist, and Certified Crop Advisor. He has a diverse agronomy background that spans retail sales and consulting at the farm gate to agronomic advising at regional, national, and international levels. Wesley was also honored in my home state of Ohio as the 2020 Certified Crop Advisor of the Year. Without further ado, I welcome Wesley Haun to the webinar.
Thank you, Don. I am honored to have this opportunity to share some information with you today concerning amending soils with Tiger products to reduce soil pH. And we'll also cover some other adverse conditions in which sulfur may be utilized. Soil pH is a great indicator of plant growth potential. Most crops require soil pH in that optimum range of 6.0 to 7.0. Yes, there are exceptions with certain crops requiring some low pH values, whereas some others fit better in a slightly alkaline condition. But soil pH influences the plant nutrients availability, as well as its deficiency, and that potential for toxicity as well. In this illustration, you've probably seen various forms of it, which indicates the relationship between soil pH and plant nutrient availability. And if you'll notice, between that range of 6 to 7, those bars for each nutrient is generally the widest in that range, and which indicates the greatest availability of those nutrients to the plant. And we have acid-forming soils, and this is due to characteristics of the parent material from which that soil was formed, whether that be through the natural weathering process, the leaching of base cations, decomposition of organic matter, as well as the application of various nitrogen fertilizers. But acid soil presents some management concerns we need to be aware of, one of which is aluminum manganese toxicity. We also have reduced plant nutrient availability, as well as reduction in microbial population, and as well as the activity of those microbes at low pH levels. And we can see a reduction in pesticide effectiveness as well. And then on the opposite range of that spectrum are alkaline soils, which are a high pH situation. We can have a reduction of availability of nutrients, and that includes both the macro as well as the micronutrients. Microbial activity is influenced, as well as an increase in volatilization of urea when surface applied. And let's identify two terms that we need to be familiar with, and the difference between alkaline versus alkali. When we mention alkaline, we're referring to soils that have a high soil pH. The term alkali may be indicating a high pH. It could be a saline situation, or possibly a sodic situation, or a combination of those three. But unfortunately, both of these terms can be used interchangeably, and which is not appropriate. Some differences in use of sulfur products. The plant nutrient sulfur, when applied strictly as a plant nutrient, is generally applied at low rates, and we're generally speaking of 20 to maybe 50 pounds per acre. But when we talk about adding sulfur as a soil amendment, we're applying at a much higher rate to influence that soil chemistry. So when we speak of amending soils, we're adding amendments or with materials added to the soil to improve its characteristics that are more conducive to root growth as well as enhancing nutrient uptake. So some adverse soil conditions that I'd like to address when we have high pHs, and those include alkaline soils. Here again, this is pH of 7.8 or higher, but oftentimes you can see some activity or adversity occur at a slightly lower, as say 7.5 as well. And then saline soil, which is a high salt content. Acidic soil has high sodium content. And then we have soils that have a combination of the two, which we refer to as saline-sodic soils, having both high salt as well as a high sodium level. So when trying to manage these soil conditions, my best advice and our best diagnostic tool is a soil sample analysis. And when you submit a soil sample and you suspect one or more of these conditions, you need to specify a specific test for either the saline or the sodic test, and we'll talk more about that moving forward. A saline soil, high pH. We have values that we need the soil pH on. We need the soil EC, which stands for electrical conductivity. We need to know the amount of free calcium or bicarbonates that are present. Preferred to have that as a percentage instead of a numerical value. And then the desired level of pH. Do you want to move the pH level or lower that pH value? We need to know if that soil is calcareous, and what we refer to that is it has high amounts of calcium carbonate or lime. We often refer to that as free lime, and there are tests that can be done in the lab as well as in the field. And when we're in the field looking at particular soil conditions, a fizz test is often conducted, which is basically taking a small soil sample and adding a few drops of vinegar, which contains acid. If they're doing a fizz test in the laboratory, they're probably going to use hydrochloric acid for that fizz test. And basically what we refer to that fizz test is a bubbling effect similar to an Alka-Seltzer. And then we have phosphorus unavailable. It's chemically bound up with calcium at a high soil pH. This graph illustrates that effect. And notice at the lower soil pH, we have a high amount of fixation due to iron. Then as we move up to that 5 to 6 range, we can have some fixation by aluminum. And then we get well above pH of 7, and we see fixation by calcium. But notice there's a zone, a very narrow zone actually, of which phosphorus is most available, and that's from about 6.5 up to about 7.2, of which we have the greatest availability potential for phosphorus. Now, trying to manage high pH soils, we can add Tiger-Sul, but the amount that we add is a function of soil texture, which is also can be a reflection of the cation exchange capacity of a given soil as well. In this chart, we have some selected ranges of changing soil pH, and that first one is going from a pH of 8.5 down to 6.5, so we're moving this 2 whole pH numbers or values. And if you've got a sandy soil, we're speaking in range of about 370 pounds of sulfur per acre. Whereas if you got a clay soil, then we need about 1,460 pounds per acre of Tiger sulfur. So as you can see, the texture has a dramatic impact on the amount of sulfur required, and this is due to the buffering capacity of the soil to make that change. These values are based upon the assumptions that sulfur product will be incorporated 6 inches deep and the soils are not calcareous. Now, saline soil conditions. We've got a high pH. We need to know the soil EC, electrical conductivity, and this can be done in a 1-to-1 ratio of soil to water, and oftentimes we would prefer to see that conducted as a saturated paste. In other words, these higher amount of soil to the amount of water that's applied, generally that consistency would be about that of a milkshake, and then measure the EC in that paste. Either way, you'll probably see a EC value of equal to or greater than 4, which indicates we've got a high salt level. And actually you can see some plant adversity situations occur even in that 2 to 4 range as well, with plants that are not very tolerant of salt conditions. So with a sodium base saturation of less than 15 in a salt situation. And salts tend to accumulate in the soil due to surface water containing the salts as a result of runoff from parking lots and man-made drainage situations here again. But all this is the result of the evapotranspiration exceeds the amount of precipitation an area receives. And as the water evaporates, it leaves behind the minerals, and here again, the accumulation of the salt. Here again, with this image, we see an area of high salt being reflected on the soil surface. The white discoloration is the salt minerals left after water has evaporated. In a saline soil, also got excess salt. The salts conduct electricity, so hence we are able to do this electrical conductivity test in the lab. And when you're in the field trying to evaluate the situation, soils look somewhat normal, but that salt reduces the water uptake by the plant. And in turn, we have a harmful effect on the plant growth, and we see a greater soil water potential increase. So under saline conditions, if you got low salt, there's a greater water cohesion between the soil particles and the roots, and therefore the plant roots are able to absorb the water. Whereas in a high salt situation, you have greater water adhesion between the soil particles, such as your clay and organic matter, but the plant roots are not able to compete and not take up water. You can have water at field capacity and the plants are wilting due to the fact that they cannot take up the water due to the adhesion between the soil particles themselves. And salt effects on the plants can be a wide range. You can have low water uptake efficiency, decreased nodulation and the nitrogen fixation within legume plants, obviously poor root growth, and a reduction of flowering as well. Moving over to the right side of that illustration, we can see a reduction in photosynthesis taking place, stress-induced DNA damage, and cellular dehydration. All these contribute to a reduction in growth and obviously a reduction in yield potential of a given crop. In saline soils, there are no chemical amendments. We just need well-drained soils or artificial drainage in those soils. What we need to do is just flush the salt out of the rooting zone. And able to do that, it's going to require 6 to 12 inches of water in excess of what the crop will need. Actually, you like to be able to manage these options to utilize salt-tolerant crops, to increase the residue and ground cover so that we reduce the evaporation potential, and irrigate early in the season and saturate that root zone. The greatest potential of damage in a salt situation obviously is during the seed germination and the early growth of the seedling stages of the plants. So if we can irrigate during the growing season, prefer to see multiple irrigation events with less water per event, but more frequent events. Here we go, I'm trying to keep that root zone wet so to increase the reactivity and the movement of that salt out of the root zone. It's more effective when you utilize overhead irrigation. As flood or fair irrigation, you have less control of water volume. Some crop sensitivity to salt. Here again, almonds, citrus, apricots, plums, celery, beans, all tend to be sensitive to salt conditions. Whereas if you can utilize crops such as alfalfa, cotton, sugar beets, potatoes, tomatoes, all these crops tend to be more markedly tolerant to salt conditions. So here again, it's another way to be able to manage these soil conditions with specific crops. Our next set of soil conditions are referred to as sodic soils. Sodic soils equals an excess amount of sodium present. It affects the water as well as nutrient uptake by a plant and adversely alters the soil physical characteristics. By altering the soil characteristics, I tried to illustrate that with this graphics. On the left side of the slide, we have soil particles with open space between them, which would be the air space within the soil, whereas on the right is more of a compacted area, and you see there's no pore space available. Well, in a sodic soil situation where it's changing the characteristics, actually the sodium causes the soil particles sort of fuse or melt together, which would be more of a solid layer, which decreases the permeability of water to move into the soil itself. Sodic soils may impact plant growth by specific toxicity to sodium-sensitive plants. We can have nutrient deficiencies or imbalances take place, as well as a high pH, and that dispersion of soil particles I alluded to earlier, which causes the poor physical condition of the soil. In sodic soils, we obviously have high sodium levels. We have poor soil structure. We have dense soil layers with very slow water permeability, as well as low soil aeration. Potential problems with sodic soils is a function of the soil texture, soil type, as well as the quality of irrigation water and the drainage potential a particular field may have, whether that's internal drainage and or surface drainage. So when is there too much sodium? There are two values from a specific soil test that we can evaluate. One is the SAR, which is SAR, which is referencing the sodium absorption ratio, which would be greater than or equal to 13. Whereas the ESP is the exchangeable sodium percentage, which is going to be equal to or greater than 15. Either one of these values on a soil test report will give us an indication of whether we have a sodic situation. And as you see on this soil test report on the right side where the CEC is listed, when we say the SAR is 13 or higher, that means 13% or more of the CEC is composed of sodium. Or if it's the ESP, which is 15 or greater, then 15% all this cation exchange will be composed of sodium, which is way too much from the standpoint of impacting soil productivity. To give you a little better illustration of the situation, and looking at this graphic of the soil particles with the negative showing and the various cations that are attached to that soil particle, and when we have the sodium displacing some of these cations, and then we have a situation where there's too much sodium present in the cation exchange. So trying to amend sodic soils, we have three options we can do. We can change the plant species to a more tolerant species, or we can change the variety within a species to a more tolerant variety, or we can change the soil. Well, as we work with various producers with these type of soil conditions, the first option they prefer to move with is changing the soil, which obviously is going to be the more difficult option to take. So two approaches to amending the soil is, one, we add calcium directly to the soil in the form of calcium sulfate, better known as gypsum. And with that addition, the calcium and the sulfate will disperse, and you get the calcium, which will displace the sodium off the cation exchange complex, move it out into the soil where it will be mobile with the soil water and can be leached out. The other option is an additive be added to the soil to dissolve the calcium carbonate that's present. And that option is like using Tiger-90 product. Here again, in the oxidation process of Tiger-90, we have gypsum or calcium sulfate that is formed. Then that calcium sulfate will dissociate, and then the calcium can be used to displace the sodium so that it can be leached out of the rooting zone. So when using Tiger-90 as a additive, we can have calcium sulfate that is formed in the oxidation process, and here again react just like adding the calcium sulfate in the previous option, whereas the calcium will displace the sodium and the sodium can be leached out of the rooting zone. And at the same time, in that oxidation process, we have sulfuric acid that is formed, hydrogens are released into the soil, therefore will reduce the soil pH at the same time. Another option is, I've had growers actually use a combination of these two options by adding calcium sulfate along with Tiger-90 to speed up the process somewhat in releasing the calcium to disperse the sodium, and at the same time start lowering the pH of the soil. Now, just be aware when trying to blend the two, make sure you are looking at adding enough of the Tiger-90 to start lowering the pH as well, or you may have to take a second step later in the process to help lower that soil pH, because almost always in a sodic situation, we will have a high pH. So, as part of amending these sodic soils, a popular question I often receive is, what is the appropriate amount of gypsum that's required to activate this reaction? Well, my old adage is, it depends. We need to know the current cation exchange of the soil, need to know the depth for which the desired change is desired, or the soil depth for the desired change in the sodic situation, and the extent of the change in the SAR value. But as a general rule, it's probably going to take anywhere from 2 to 5 tons per acre of gypsum to activate this reactivity. Then another soil situation is a saline-sodic soil. This is a soil that has both of these conditions at the same time. We have an excessive salt concentration, we have an excessive sodium concentration, and an EC value that's equal to or greater than 4, and an ESP greater than 15%, or a SAR that's greater than 13, and a high soil pH, all occurring at the same time. So as we evaluate the opportunity we have here with Tiger-Sulphur, with elemental sulfur in the presence of oxygen and the presence of water with bacteria, we have sulfuric acid created. That's the H2SO4. Then that sulfuric acid will react with the calcium carbonate that's in the soil and produce the calcium sulfate along with carbonic acid. Carbonic acid is a weak acid. It will dissociate into water and carbon dioxide. So here again, the main part of this reaction is the formation of sulfuric acid, which will reduce soil pH. So in comparing other products that will supply us with 1 pound of soluble calcium to help displace the sodium, gypsum at 100% purity is going to take about 4.3 pounds to give us 1 pound of calcium, whereas with sulfur, with 100% purity, you're going to take about 0.8 pounds to give us 1 pound of soluble calcium. So you can see there is a variation between various products to give us the equivalent amount of calcium that we need to displace the sodium. So in summary, sulfur is an essential nutrient for plant growth. Tiger products, especially Tiger 90, is a product of choice utilized as a soil amendment. And then we have 4 primary soil conditions. The alkaline soil has a high soil pH. A saline soil has high salt content. A sodic soil has high sodium content. And our saline-sodic combination has both conditions, high salt and high sodium present. Tiger products are effective for soils primarily with an alkaline soil, which is high pH, and a sodic soil, which is high sodium. We do not have reactivity with saline conditions because saline is salt. We just need to leach that out of the profile with water. So for further information on this topic, I encourage you to go to our website. I have written a technical bulletin on this subject giving some more specific details. Due to the time constraints we have today, just hit the high points of this subject matter. And the name of that bulletin is Amending Soil with Tiger 90 CR Sulphur. If you have other questions, you're encouraged to contact your local account manager, or you're welcome to contact me directly through the email shown on the screen. So with that, I thank you, and we will move to the question and answer session.
Wesley, as we get ready to begin our question and answer period, I would remind all of our listeners that you can submit a question by clicking on the Ask a Question icon, and we will attempt to answer your questions today. In the event we run out of time, all of your questions will be answered by email. So with that, we'll go to our first question. Is it economical to add sufficient sulfur to reduce the pH?
Interesting question there, Don. My old adage is, it depends. We need to know some information as it relates to the amount of pH change that's required, the soil texture that is present, as well as the soil calcareous. And then, as we assess the amount of sulfur that may be added, is the crop value as it relates to the specific crop and plan for a given field. So with that, remember in my presentation I referenced a chart that gave the amount of sulfur required to lower the pH based upon soil texture. And to change that pH value, if I recall correctly, 2 whole points. A sandy soil required approximately 400 pounds per acre, whereas if it's a clay-based soil, it's approximately 1,500 pounds. Assess the amount that's required to change that pH versus the value of the product and the crop it will be applied. So with that, I hope that guides you somewhat in making that decision.
Thank you, Wes, for that answer. Our next question, can I add acid to irrigation water to lower soil pH?
Yes, acid can be added to the irrigation water. It's actually injected into the water line as it goes out to the field. Generally, it's either sulfuric acid or infuric acid that's generally added. I rather prefer to consider this as treating the water rather than treating the soil. With injecting the acid into the irrigation line, we're neutralizing any bicarbonates and minerals that's in the water prior to applying to the field. Probably will not have enough acid in the irrigation water to really treat the soil sufficiently.
Thank you, Wesley. Our next question, always been told to apply gypsum to improve salt soils. Why is that not good method?
Interesting question there. If you remember in the presentation, we was talking about the salt. No chemical addition is required to remove the salt. What we really need is sufficient water to apply to the field with good internal drainage, whether is the soil well drained or do we have artificial drainage there to move the water out of the rooting zone. By adding sufficient water, we move the salts down through the profile and out of the rooting zone. Therefore, no other compounds are needed to remove the salt. And actually, if you're applying gypsum to a salt situation, actually gypsum is a salt. So you're adding salt to a salt situation, so it does not improve.
Thank you, Wes. Another question, how can I determine amount of bicarbonates in soil to calculate sulfur needs?
Good question. And that's certainly a value we need to know in order to make any type of calculation. And first, submit a soil sample to the lab and specifically ask for the percent carbonates, and some labs listed as free lime listed. So here again, you need to list that separately so that they will give that to you as a percentage. And then once we know that percentage, we can make the adjustment accordingly. We need to keep in mind though, for each 1% of bicarbonates present will require approximately 3 tons of sulfur per acre. So this becomes an economical question from the standpoint of being sufficiently able to adjust the bicarbonates, because we have to neutralize the bicarbs before we can lower the pH. So hopefully that answers the question sufficiently.
Thank you, Wes. That's all the questions that we have for now. Again, if you have questions, please click on that icon and we will respond to you. And we thank you for your time today. And if you have additional questions, please feel free to contact your regional account manager or Wesley direct with your questions.